One last topic in bivariate regression is the regression equation we use for variables whose raw scores have been converted to z-scores. We call this variation of regression the standardized regression equation. When scores on the predictor and the criterion are in standard score form, the basic bivariate regression equation changes to zy hat is equal to beta times the z-score of x. In this formula, zy hat is the predicted z-score on y, and the regression line connects all the predicted z-scores of y when we use z-scores of x to make our prediction. Also, the constant or the intercept disappears from the equation. This is because regression lines must pass through the mean of x and the mean of y. Because the mean z-score for x and for y each equals 0, this means the standardized regression line passes through the origin of the graph. Thus, the y-intercept is always 0 when the z-score of x equals 0. In the standardized regression formula, we use beta instead of b, and the name changes from the regression coefficient to the standardized regression coefficient. It is used to multiply or weight z-scores on x in order to predict z-scores on y. Beta remains the slope of the regression line as discussed in the previous class when we talked about the regression coefficient. An important relationship that is unique to the standardized regression equation is that beta equals r, or the correlation of the two variables. Thus, the correlation of x and y can be thought of as the slope of the standardized regression line for the two variables. Another important way of thinking of beta is that it equals the change in the predicted z-score of y when the z-score of x increases by one z-score. In our example that we followed previously in this section, the correlation between x and y equals 0.43, which means beta also equals 0.43. Let's compute the predicted z-score of y when the z-score of x equals 0.50. Our regression equation, our standardized regression equation, is zy hat is equal to 0.43 times 0.5, or 0.215. Thus, a z-score on x equals 0.5 predicts a z-score on y equal to 0.215. To say this in another way, a z-score, a score of 0.5 standard deviation units above the mean on x predicts a score that corresponds to 0.215 standard deviation units above the mean on y. If we increase the z-score on x by one z-score to 1.5, our new formula is zy hat is equal to 0.43 times 1.5, which is equal to 0.645. Thus, it predicts a z-score equal to 0.645 on y. Please note that the difference between the two predicted z-scores equals 0.43, or the value of beta. It is critical to remember that a change of one z-score on x is actually a change of one standard deviation in the raw score of x. Because beta is merely a linear transformation of the regression coefficient, the null hypothesis of b equals 0 is identical to the null hypothesis of beta equals 0 in the standardized regression equation. Thus, the null hypothesis for both formulas is that the predictor fails to predict variance in the criterion. This is tested with a t-test, which is computed by dividing beta by the standard error of beta, and tested with degrees of freedom equal to n minus p, or n minus 1. This t for beta is usually not computed because it is identical for the t computed for b. Once we have found that we can accept or reject the null hypothesis for b, we have simultaneously tested the null hypothesis for beta. The interpretation of a significant beta would be the same as discussed for the bivariate regression in the previous example. We would conclude that BDI scores at intake are significant predictors of suicidal intensity ratings in the future. As based on the original finding that R equals 0.43 and R squared equals 0.1849, we would say that BDI scores can help to predict 18.5% of the variance in the criterion. Also, because B and R are positive, we would say that increases in depression scores predict increases in suicidal intensity ratings.